Question 2 looks at waves and sound waves. The first thing we get is a slinky spring that's being used to model a sound wave. It's a longitudinal wave because the oscillations are parallel to the direction of energy transfer, to the direction of wave travel. If we have a look at this point to this point, it's between two compressions, and that is a wavelength. Where the coils of the spring are pushed closely together, they're compressed, is a compression, and where the particles, where the links of the spring are far apart, that is a rarefaction. Moving up to the next one, 2.2, what type of wave is a sound wave? Well, it's longitudinal because it's vibrations of particles that vibrate parallel to the direction of wave transfer, so longitudinal. So next we've got two students that are measuring the speed of sound in air. So what they're probably going to do is clap the two bricks together. When the person sees the bricks come together, he's going to start the stopwatch. The sound is going to travel all the way to the wall. It's going to bounce off, and then by the time it gets back here, the guy will stop the stopwatch, and they'll be able to use speed equals distance divided by time to calculate how long it takes. One thing to watch out is you're probably going to measure the distance from here to here. That's the distance between the students and the wall. That's not the distance the sound wave travels. The sound wave travels twice this distance. So let's see what we've got. Describe how they can determine the speed of sound. So they will clap bricks together. Starting the stopwatch. When they see them hit each other, they'll stop the stopwatch when they hear the echo. So an echo is sound bouncing off something. You can then use a tape or trundle wheel to measure the distance to the wall. Double that to give distance travelled by the sounds. You then use speed equals distance divided by time. That will give you the speed, and finally repeat it, take a mean, having discarded any anomalies.